All right, so today we're working on finite element analysis for the trailing arm. I figured this would be the easiest place to run structural analysis on because it's just a simple beam with two connection points and then a force load right in the center. So it seemed like that was a good place to start. So one of the first things that I needed to do is record the critical dimensions for this part, and that includes the weight and the total length and the shock mount. So the length was 72 inches and the shock mount is 36 inches from the pivot. So that dimension ratio makes the force calculation super simple. So I found this simple design diagram here explaining how force loads are calculated on a beam like this. So if you have a length and a total length of the trailing arm, and then a shock mount location, and then the corner weight, you can calculate the spring load in the center of the part. And the spring load is not equal to the corner weight. It's a ratio. And that ratio is F1 times L1 plus F2 times L2. And what that means is you're canceling out the torque, so you can run static analysis on a part like this. And the great thing about statics is all the forces neutralize each other because the part in the simulation is static, meaning it's not moving. So if you have a corner weight of 2,500 pounds and then a spring weight, it will be 5,000 pounds. Then I'm using another calculator here to double check that. So talking about that corner weight, 2,500 pounds is a lot. I don't expect the vehicle to actually be 10,000 pounds, but what I wanted to do was make sure that I was calculating for worst case, which would be fully loaded vehicle with 4 passengers and a fuel tank. So it's a nice round number to start with. And then as time goes on, I'll probably walk that weight back. So I heard from a video once that in the off-road engineering industry, they usually simulate for a 5G load. And that makes sense. I mean, the G-force any higher than that would just break your bones. And it seems like a good standard. It's a reasonable place to start. So that's what I'm going to start with. And then there's this really cool tool called SimScale. And this allows you to run finite element analysis online. And it's free. So if you wanted to start with this, it'd be free for you too. And the great thing about this tool is it's incredibly fast, way faster than running FEA on your local machine. This sends it to a remote server, and it makes processing 10 times faster than anything I've ever experienced. Like in the SolidWorks embedded FEA tool, it takes forever, but this one is really, really fast and really simple. And most FEA tools like this have a similar user interface, so it's pretty easy to get started with something like this. And the units in here are defaulted to metric, and I like to keep it that way because there's a lot of material properties that are quoted metric, and it's easy to convert them from pound force to newtons. So there's another resource called MatWeb, and it's a database of every material under the sun. So I want to look up the specs of 7075 aluminum, and I'm checking to see if 74 weld calls out the heat treating spec. They don't, but I'm pretty sure it's 7075 T6, which should sound familiar because 6061 T6 is an aircraft grade aluminum that everybody uses everywhere. 7075 is heat treated, so it's quite a bit stronger. But they don't have that material in SimScale, so I'm just going to run regular aluminum. So now I'm checking the delta between 7075 Young's modulus and the Young's modulus quoted in SimScale, and it's a difference of only 1. And so most of these FEA tools, you have a body, and then you have supports, and then you have a force, and you need to set all of those up. So what I need to do first is set up a fixed support, and I'm putting the first one at the pivot of the trailing arm, and then I'm putting another one at the end of the trailing arm. But I'm going to put my force load right in the center where the part shock mount is. And this is an isolated static calculation where I'm omitting all the other aspects of the vehicle and the forces imparted. I'm just looking at the forces imparted on this part, and in an idealized case, the only forces on this part would be experienced in the 2 fixed support where it interfaces with the rest of the assembly, and then the shock load right in the center. So I need to put this shock load at the corner weight times 5, which ended up being 90 kilonewtons. That 90 kilonewtons is a lot, but this is going to be a really strong part. So what I just did here is a mesh, and this is a critical aspect of FEA where you run a mesh and it creates these little nodes on the part, and these nodes interact with each other in the simulation. And so it's a way to take a complex geometry and break it up into a series of little triangle prisms. And then when it makes a calculation, it's a lot easier for the computer to do. So the scaling factor that you're seeing here, think of this like a caricature of what the part would actually experience. This is displacement with a visual amplification factor of 50. So this part is only going to displace a few micrometers, but the simulation is showing me a scaling factor of that. So I want to look at two things, displacement and stress on the part. And I need to make sure that the stress, the highest stress, this part, is not greater than the yield strength of aluminum. So the way to do that is you pick one of these hot spots on the color and you see what that stress is measured in pascals. So now I'm going to copy my FEA results to the material properties of 7075 and then see what we kind of come up with. So the von Mies stress here is 98 megapascals and the ultimate strength is 572 megapascals. So the safety factor here is the ultimate strength divided by the peak stress that the part experiences. And I got a safety factor of 5.8, which means that the part is about twice as strong as it needs to be. And what I really want is a safety factor of something more like 2. That would be reasonable. So this part is about twice as strong as it needs to be. Well, technically it's 5 times stronger than it needs to be, but I can knock that safety factor down by chipping away at this part. But this part was not that heavy. It was only about 100 pounds. And I mean, it's a 6-foot long piece of aluminum, so that's okay with me. And I'm not simulating any side loads on this. I don't know what those loads would be in terms of corner weight force, but I think the beefier, the better on this one. So now I found another hotspot here in that red. What you're seeing there, that's what happens when you have a sharp corner on the inside of a geometry. And that sharp corner represents the groove for the C-clip. And you see on this part, everywhere I have pocket cuts, I have fillets and radiuses all over the place to get rid of those sharp corners. So now this rainbow looking graphic shows displacement, and the red part at the center moves the most. That's the trailing arm. What we're looking at here is the rear lower control arm. And this assembly, but SimScale doesn't like assemblies. At least I haven't figured out how to get them to work every time. What's a lot easier is to take the parts that you need to save and save them as a new part file and then import that entire body into SimScale. So now I have these 2 parts in the assembly. I'm going to save that assembly as a part and rename it FEA and make sure I don't use it anywhere else. The first time I did this, it defaulted to only saving the surfaces, and that doesn't quite work because you need to save as a body. So you just have to adjust your settings, and now you can see this part is hollow, so I'm going to resave it as a body. Then I'm going to put this part back in the FEA tool. Now the body is a solid, it's ready to go back into SimScale. So part of the shock mount was not perfectly in the center. It's offset slightly, so my force calculation ratio is going to change a little bit, but it ended up being similar. So for the purpose of this calculation, I just made it the same. So I have a 32-inch total length, 17-inch shock mount location, which gives me a ratio of around 2. And same story here, the corner weight is assumed to be 2,500 pounds, and then the shock load in the center is going to be double that. So now I can check those dimensions again, 32 and 17 to get that ratio. This part's pretty light and only weighs 3,500 pounds. And so the sprung corner weight is about half of that static load in the center. So that gives me 85 kilonewtons compared to 90, but I'm just going to run it at 90 again. So same story, selecting my material, and then I select my boundary conditions, which are 2 fixed supports, and then a force load right in the center on those 2 mounting locations. Negative 90 kilonewtons, so that's the force pointing down, and then this part is ready to run the mesh again. So this is what the results look like. There was a ton of stress in that part. It's pretty strong. You can see the caricature displacement, but I'm really happy with the material thicknesses here. It's not too heavy and the stress is fairly low throughout the part. There's a little bit of twisting moment because they have those pocket cuts opposing each other. I'm not really sure why I did that, but I don't know if it's necessary. I ended up with a safety factor of 7, which is super great, super duper strong. I want this part to be really strong. So I'm going to try a dynamic simulation next. This is allowing you to impart a force over a certain time scale, but I couldn't figure out where that input was on SimScale. So I'm going to have to reach out to their support team to make sure I set this up correctly. So I'm trying a new type of support here. I'm trying a hinge support on the pivot point of the trailing arm, and then a fixed support on the shock mount. And then I'm going to impart the force load at the end. I think this is a slightly more accurate representation of what the part is going to be experiencing, where the far end has the force from the world, and then the shocks are simulated as being fixed because they're pushing against the center of the part. And then the far end is the pivot point. So that hinge support allowed me to have a lot more displacement which I think is a good thing. And this is a probably more accurate model. I think this is probably a more accurate way to model this. So you can see the movement at the end of the part. I found this really cool animation feature, which makes the whole thing look pretty nuts. You can see exactly how the part moves under load, and the peak stress on this ended up being the same as what I did in the other simulation. It was slightly different, but within a margin of error. And that's how you do FEA.